Okay, let's begin our second session of the day. I'm delighted to introduce Professor Demba. Demba received his bachelor's degree in electrical engineering from the University of Maryland, College Park, and then he did a master's and PhD in electrical engineering and computer science with a minor in mathematics at MIT. He was an intern with Microsoft Research during his graduate studies, and then a postdoctoral associate with MIT Harvard Neurosciences Statistics Research Laboratory. He is currently an associate professor of electrical engineering and bioengineering at Harvard University, and he directs the CRISP group there, which work on computation, representation, and inference in signal processing. He's also a Sloan Fellow, and his research interests are very broad and deep, working on high-dimensional statistics, optimization, and dynamical modeling with applications to both neuroscience and multimedia signal processing. And his recent interests are in the connections between neural networks and sparse signal processing, and that's what we'll be hearing about today in his talk on learning deeply sparse signal representations.
Thank you, Gal, for the introduction. It's great to be here. I want to first thank the organizers for inviting me to share some of my work. And I'm simply going to name the ones that I've interacted with, Gal, who just introduced me, Jeremiah Sulam, who I've met in person, Soledad Villar, and Adam Charles. So what I want to talk to you about is something that I've been super intrigued with, and this actually started by reading some papers by Jeremiah and some of his collaborators, is about this connection between ReLU networks and sparse signal processing. Okay, and the best way to introduce this, or at least a perspective on what I'm going to be talking about, is through this following picture here. Okay, so one thing I've proposed in a paper that I will cite at the end of this talk, and that's been published in the Transactions on Signal Processing, is suppose I let you generate data in the following manner. I'll let you start with a sparse vector, X here, that I've drawn with sparsity 1. It could have more sparsity. I make it go through a sequence of transformations. For the sake of visualization, I'm only showing 2 transformations here, and you generate data Y in this fashion. The question I had been interested in, or I have been interested in for a few years now, and I'll tell you the reason why, and it has to do with the second part of this slide, is given data that is generated in this fashion, first of all, what are conditions on the intermediate matrices and what I call the intermediate representations, which are the output of each of the successive transformations, such that I can, in an unsupervised fashion, meaning only given the data Y, learn the matrices and the associated latent representations, the outputs of each transformation. And number 2, how much data do I need to actually learn these matrices? So why have I been interested in this question? And I'm going to lay all of this out during the talk, but this is just to give you a big idea for a couple of reasons. So one has to do with artificial neural networks, and the other one has to do with actual neural networks in the brain. Let me first talk about artificial neural networks. So what I want to claim, and those of you who work in this area will realize that this is a simplification, but it will suffice for the point that I want to make. What I want to claim is that there's a one-to-one mapping between learning these matrices A2 and A1, given data generated according to them, and training what I call this 2-layer tied autoencoder. So in deep learning, you feed in the data Y, it goes through an encoding process, and through matrices A2 and A1, they're transposed, which if you notice are related to the matrices in this generative model. At the output of each of these encoders, you get an estimate of the latent representation X, and you use that to reconstruct. So what we would do in deep learning is to train the neural network on the right-hand side here using backprop by minimizing the MSE between its input and its output. So interesting questions would be, could you show that if you generated data according to the model on the left here, and you train your tied neural network by backprop, that the neural network would converge to the weights that you use to generate the data? As far as I know, this is a question that has not been answered in deep learning yet. Number 2, how much data would I need to train that autoencoder? As far as I know, it has not been answered. One question that I know has been answered, and I'll cite the paper later, is that in the shallow case where I only want to learn one dictionary, there's been work showing that with infinite data, a neural network trained by backprop could converge to a neighborhood of the true weights that generated the data. Okay, now I'm not going to answer the question that I really would like to answer, but I'm going to take a back door. I'm going to say the following. Well, this model here that starts with a sparse vector and generates a bunch of representations culminating in my observations y. The problem of learning the matrices A2 and A1 in this case, this is a generalization of the classical dictionary learning problem in signal processing where I only have one of these matrices to learn. There's a lot of theory there. If I could generalize that theory to the case of multiple transformations and come up with conditions on these matrices and the intermediate representations that guarantee that I can learn the dictionary, I could use that as insights as to how much data the associated autoencoder would need to be learned by backprop, as well as what conditions should the matrices satisfy so that I can hope that the autoencoder will learn this. One portion that I'm not going to talk about, which is related to my interest, is that it turns out actually that what I'm calling this deep sparse coding model here is actually related to hierarchical models in neuroscience of how we believe the brain may process sensory information. So you start with an image Y, a transformation A2 or its transpose gives you a sparse representation, and that is successively sparsified at different layers of the brain. But I'm not going to touch upon that today. So to summarize in the next slide, I'm going to tell you what I would like to do today. I want to consider the problem of learning dictionaries in what I call this deep sparse coding model. What is known is the following, that given the matrices in that model, ReLU networks in some sense are equivalent to sequential sparse coding. I will cite references later, but this is related to work that Jeremias and his colleagues have worked a lot on. My goal is, what are the conditions such that given Y, data generated according to that model, and assuming the matrices A's are not convolutions, but dense matrices, what are conditions such that given the Y's, I can learn all of the matrices in that deep sparse coding model? Number two, how much data do I need to learn all the matrices in that deep sparse coding model? What are the potential implications of this? The potential implications are that these conditions could, number one, give guidelines as to how to design deep ReLU networks, such as the one on the right-hand side here. And number two, it could give some insight as to the amount of data that we need to train what I call these tied autoencoders with multiple different sets of weights. Great. All right, so to start, I want to give you some background on this connection between ReLU networks, or the ReLU nonlinearity, and sparse approximation. I'm going to start there and move to the connection between training autoencoders and classical shallow dictionary learning, and then I'm going to get into my deep sparse coding model and dictionary learning for that setting. All right, so I want you to first consider the optimization problem that is at the top of the slide here on the left. So the problem is a rather benign one, but this is where the journey started for me. So I give you a scalar valued quantity Y. And I ask you, what is the non-negative real number X that solves this optimization problem, which minimizes the distance between Y and X squared, plus lambda times some absolute value, which because X is non-negative, is just X in this particular case. So a lot of you that work in sparse signal processing, or even if you do not, but if you work in machine learning, you could think about this as a one-dimensional version of lasso. It turns out that the solution to this is to take Y, subtract lambda from it, and compare that to 0. If it's greater than 0, I will keep Y minus lambda, otherwise I will set it to 0. In deep learning, we would call this operation the ReLU of Y minus lambda. And I've drawn this visually here, where Y is on the x-axis, and the operation you perform is Y minus lambda ReLU. In signal processing, so in classical signal processing, the more familiar version of this is when we drop the non-negativity constraint on X, and we end up with what is called the soft thresholding operation. In neural networks lingo, you think about this as a two-sided ReLU. This is a rather benign example because it's in one dimension. Why am I claiming that there's a relationship between ReLU networks and sparse approximation? Let's move to the case where X now lives in more than one dimension. And for the sake of simplifying the discussion first, allow me to assume that I have a transformation A that is in isometry. Its columns are orthogonal to each other and they're normalized to 1. And now I'm going to ask, what is the vector X that solves this lasso problem, assuming that A is an isometry. And I did not put it here in the slide, but first I'm going to assume that the entries of X are element-wise non-negative. Well, it turns out that because A is an isometry, here's what I can do. I can replace the least squares component of this loss here by A transpose Y minus X, which means that the X's separate and that I've reduced to one-dimensional, I reduced to a sequence of one-dimensional problems similar to the ones that I've showed you earlier. So here's what I want to claim here, that the solution to this optimization problem is equivalent to taking the data Y, projecting it onto each of the columns of A, subtracting lambda from it, and doing a soft thresholding operation when X is arbitrary, and an element-wise ReLU when the entries of X are non-negative. So I claim that if you give me A and it's an orthogonal matrix, you can show mathematically that the process of obtaining X that solves this optimization problem is a one-layer ReLU net where the weights of the networks are related to A here, and the nonlinearity comes from the sparsity approximation. So this is where the journey began for me. You might say that this restriction to A orthogonal is very restrictive. It turns out, again, related to some work that we have done in our group and also Jeremiah's has worked on, it turns out that when A is not orthogonal, well, you could choose to solve for X using a proximal gradient algorithm where you perform gradient descent on the squared loss part, and then you perform a proximal mapping, which is equivalent to applying soft thresholding to the gradient descent iterates, which I'm calling X of T here. So T are the different iterates of an algorithm whose goal is to solve for the solution to this optimization problem here on top when the matrix A is not an isometry. So the punchline being here that this equivalence between solving for X, that is the solution of this sparse approximation problem, and thinking about that as a neural network with ReLU nonlinearities generalizes to the case when A is not an isometry. So here I've assumed that I've given you A. What is the connection to dictionary learning? Let's talk about that in the next few slides. Before I go there, there's a bunch of work, and if I'm missing your work on this slide, it's not on purpose, apologies, but this is where the journey started for me. There's a bunch of work that has thought about this connection in the L0 setting, although they don't talk about that in those particular words. My friend Ankit Patel and Rich Baranyuk at Rice University have thought about this. As I've mentioned, Jeremiah Sulam and some of his collaborators have written a bunch of nice papers on this connection in the convolutional setting. Given the weights, how can you make this relationship between ReLU networks and sparse approximation in a convolutional sparse coding generative model that is deep? Okay, what is the connection to dictionary learning? The connection to dictionary learning is the following. So one thing that I want to point out here is that a lot of this work, before I began working on this, and perhaps there's new work that has shown up that I'm not aware of, a lot of this work was concerned with, given the weights, what is the connection between the inference step of a neural network and sparse approximation? What I was interested in is in questions of dictionary learning. How do I actually learn the weights? And can I make statements as to how much data and conditions on the dictionary, such as I can learn the weight using dictionary learning, and then translating that to some statements about the associated autoencoders. But what is this connection between what I call shallow dictionary learning and autoencoders? Let me walk you through my notation here. So A is the matrix that I'm interested in here. And again, for the sake of making these points very clear, allow me to assume that A is an isometry. This is not a restrictive assumption. So I have a matrix Y here, the columns of which, n columns, each column of the matrix Y is an example that I can use for training. Think of each column of the matrix Y, for example, as an image in the ImageNet dataset. Associated with each column of the matrix Y, there's a column of the matrix X, which is the latent representation for that column. It is a sparse vector that allows me to generate that column of the matrix Y. What is the goal of shallow dictionary learning, what I'm calling classical dictionary learning? The goal is only given Y. I want to learn A and I want to learn X. Okay. One way people solve this is to the optimization problem that I've written here. I want to find, I'm abusing notation here. This L1 norm of the matrix here means an element-wise L1 norm of each of the entries. I want to find the A and the X that minimize the L1 norm of each of the X's subject to the constraints that Y equals AX for each column and subject to this normalization constraint on the columns of A. And why do we normalize? Is because without constraining A or X, there's an ambiguity here in the representation. How do people typically solve this? This is a non-convex optimization problem because of the presence of the product between A and X. How do people solve this? Using a method that's called alternating minimization. I'm going to start with a guess of the matrix A. Suppose some oracle gave you a guess of A, right? Using that guess, I'm going to solve for the best sparse codes that I can get, okay? And assume that that oracle also satisfies this orthonormality constraints. In unconstrained form, I can write down that optimization problem like this. Minimizing for each X, least squares reconstruction loss, plus a penalty that enforces sparsity. And this lambda t here is important because it is iteration dependent. If you believe the story I told you earlier, this process of given A, orthonormal in this case, and finding the latent representation is equivalent to what I'm calling this encoder, which is a one-layer ReLU net with biases here that depends on the penalty in the optimization here. It's an alternating minimization algorithm. What is the second step of the alternation? The second step of the alternation is, well, now, given my new estimates of these sparse codes that I obtained using my guess AT, I'm now going to update the matrix A by solving a least squares problem. And that I think of as the decoder in a two-layer auto-encoder. So what I'm claiming, and some work has shown this, is that doing dictionary learning here, there's a one-to-one mapping between that problem and training the two-layer autoencoder on the right-hand side here with tide weights by backpropagation. And therefore that using theoretical results from dictionary learning here could at least give us some insight as to how much data might be necessary to train the autoencoder here and conditions on the matrix A such that we could hope that an autoencoder trained by backprop could actually converge to those weights. So there's a lot of work in signal processing on the complexity of shallow dictionary learning. So give me data Y that are generated according to this equation here. Given different assumptions on A and different assumptions on X, there's a string of work on learning the dictionary and learning the sparse representation. Again, I might be missing some people's work here, and I apologize for that. The only work that I'm aware of that has considered the problem of training the shallow autoencoder here for dictionary learning is work that came out last year by these authors. Very nice work, and it assumes an infinite amount of data. So which goes back to the point that I made earlier, that in dictionary learning, we have finite sample complexity results on the amount of data needed to learn the dictionaries. And I want to generalize those to my deep model and hope that it gives me some insight as to how much data the associated autoencoders would take to train. Okay, so, and let me point out something before I move to the next slide here. So at the end of the talk, I have a reference to my paper where I detail these ideas. I'm not going to spend too much time on some of the technical details and intricacies. I'm just trying to lay down the big picture of what I've been thinking about here and some interesting directions that I think might be worth thinking about in the future. Okay, so results in classical dictionary learning look like this, and I'm going to follow on this paper here by Ankit Agarwal. That was published in 2016. The results look like this. So under some regularity assumptions, the results say that if you give me an amount of data that is proportional to R here is the dimensionality of the sparse vector that you're interested in, S is the sparsity, the number of non-zero entries of that vector, assuming you give me this amount of data, this alternating minimization algorithm with high probability will converge exponentially to the true dictionary under the following key assumptions. RIP, restricted isometry property on the matrix A. I'll talk about later what that means, but basically this says that restricted to sparse vector, your matrix looks like an orthonormal operator. And basically this is related to preserving the norms of the vectors that are fed into the input. Another important condition is that the noise. So when you take a guess of the dictionary that is not the true dictionary, that's equivalent to introducing noise in your sparse coding problem. But as you get closer and closer to the true dictionary, the noise should go to zero. That's what this second assumption says. And lastly, which is something that I think is not thought about a lot in deep learning, is that you need a good initialization for the dictionary, for this algorithm to work and to have these guarantees. So now I want to move on to, in the deep case, in my deep sparse coding model, how can we generalize these results? Okay. So let me first talk about what I'm calling this deep sparse coding model. So it's a generalization of the y-ax equals ax model that I showed you earlier. Again, excuse me. Again, what I want you to do here is just to take a column of the matrix Y here, which is equivalent to taking a column of the matrix X. That's how you generate examples. And how you're generating examples, I'm going to start with the sparse vector X. I'm going to let it go through a sequence of sparse transformations, A1, A2, except for the last transformation. So I'm showing you this in picture at the bottom here for the case where I have 3 transformations. So I start with the one sparse vector here. It goes to a first transformation, A1, and A1 is a matrix such that its columns are sparse. It goes to another transformation, A2. A2 is a matrix such that its columns are also sparse. And it then goes to a final transformation, A3, that gives me the data that I can use for training Y. And what's important in this picture, I don't want you to focus on the fact that I'm pinching every time in the representation. What's important in some of the stuff that I'm going to be talking about is that I'm forcing the intermediate representations before generating my image Y to be sparse. And I'm also forcing the columns of the matrix A to have sparse columns. Now, this is related, again, to some work done by Jeremias and collaborators, where my conditions here on wanting the representations to be sparse at each point and doing that by forcing the columns of the matrix, intermediate matrices to be sparse, it's a sufficient condition. It's not a necessary one. There's an idea of co-sparsity there in signal processing that says that, hey, it might not be that I need these matrices to be sparse, but that's the setup that I'm going to be dealing with here. And I think from a practical perspective, one reason why this is interesting is that particularly for practitioners of deep learning, there's been a lot of work on weight sparsification. So it's interesting that one of the conditions that comes up here is making some of these weights sparse in the generative model. Okay, so what's my goal? My goal basically is a deep generalization of the shallow dictionary learning problem that I showed you earlier. I want to find the sparse vectors X that I want to minimize sparsity, and L1 here is a relaxation of L0 basically, such that Y, the data that I have for training, satisfies this linear relationship here. And my goal is to minimize this objective function subject to these constraints so as to find not only the sparse representation X, but all of the dictionaries that would have generated the Y. And again, as in the shallow case, we have this normalization constraint here that is for the sake of not having ambiguity between the sparse representations and the columns of the matrix itself. So how I'm going to do this? I mean, you've probably guessed how I'm going to do this. I'm going to do this in a sequential fashion. What do I mean? So let's take the example when I only have 2 dictionaries to learn. So capital L equals 2. So for capital L equals 2, I need to learn A1 and A2. And remember that in my generative model, I have the assumption that A1 has sparse columns. And I'm going to call the combined matrix A2 times A1 using this notation here, A1 arrow 2. Okay? So here's what I'm going to do. I'm first going to learn the product matrix using classical shallow dictionary learning, right? Because X is sparse, I can use shallow dictionary learning and alternating minimization to learn the product matrix. That's this first step here. So I'm going to minimize sparsity such that Y satisfies this linear relationship here in terms of the product dictionary A2 times A1. If I can show that that will converge after a certain number of iterations or after infinitely many iterations, this means that I would have recovered the product dictionary. And you should guess now why I assume that the columns of the matrix A1 were sparse, because if I've learned the product dictionary now, here's what I can do next. I can use the product dictionary at convergence and then factorize this into a matrix A2 and a matrix A1 whose columns are sparse, which is yet again another shallow dictionary learning problem. This is the algorithm, okay? Now, again, I have the following results in my paper, which says that given close enough initialization of all of the dictionaries with high probability. There's two conditions. The first one says that the complexity of the learning, and I'm going to summarize this pictorially in the next slide, which I think is a nice way to display it. The first condition says that the complexity, the amount of examples you need to learn all of the dictionaries, depends on the dimension of the sparse vector, at the sparsity of the embeddings at the deepest layer, and the dimension of the vector. So that's what the first condition here says. Complexity depends on the sparsity at the deepest layer and the number of hidden nodes at that layer. And what's interesting about this particular algorithm that I just presented is that this algorithm gives you some constraint that the number of hidden nodes as the successive layers should satisfy. This is what I meant at the beginning of my talk when I said that by studying this deep dictionary learning problem, it might give us some prescriptions as to how we can build deep autoencoders with tied layers. Let me show what this theorem means pictorially in the next slides, or what I think some of its implications are. Okay, so again, two matrices to learn, two-layer deep sparse coding models with the assumption that A1 is sparse, A2 can be dense. All I give you is Y. So here's what the theorem says. The theorem says that as a practitioner, here's what you would do. Y lives in D dimensions. You pick R2, the number of units in the first hidden layer. Okay, so you start with Y here, and you pick R2, the number of units in the first hidden layer, and the associated matrix A2 here could be a dense matrix. Right, the theorem's second condition in the theorem, which relates to different layers, says that one sufficient condition to be able to do dictionary learning here using my sequential alternating minimization algorithm is that the matrix A1 here should be a sparse matrix. Sparsity of ways connecting the first layer to the second layer. Okay, and that the size of the second layer here should be proportional to the size of the layer preceding it and the sparsity of the ways connecting them. And the theorem says that as long as I can guarantee this and I reconstruct, right, this is the connection with the autoencoder, as long as I can guarantee these conditions and I reconstruct, the amount of data that I need is related to the sparsity of the representation at the deepest layer of the encoder and the dimensionality of the number of hidden units at the deepest layer of the encoder. So let me just repeat this briefly. So you start with the Y, you pick the dimension of the first layer. The first layer can be dense. The next layer has to be sparse. The dimensionality of the second layer can expand. Actually, the theorem says that it should expand in a way that depends on the dimensionality of the layer preceding it and the sparsity of the weights. And then you reconstruct using your autoencoder. So one thing I want to make clear here is that I'm not suggesting that my results are results about what I call the autoencoder associated with this deep sparse coding model. I'm suggesting that by studying this deep sparse coding model and the fact that you can provably show that there's an associated autoencoder with this deep sparse coding model, and using insights from studying the deep sparse coding model can tell us things such as, this is how much data I need to train this deep tied autoencoder, and some constraint that the weights of this deep tied autoencoder should satisfy. That's the claim that I'm making. Okay, so I'm just going to give you a quick sketch of how the proof works. Again, if I go back to my algorithm here, let me just go back a few slides. This is a sequential alternating minimization algorithm. I first learned the product matrix using shallow dictionary learning. After I've learned it, I repeat this, and then I learn each of the matrices. This is what I call sequential dictionary learning. So you can guess that one way I prove one of the results in my paper is to start with results on shallow dictionary learning and apply them sequentially using induction. That's basically a sketch of how my proof works. And the sequential application of the result is what gives you the constraint that successive hidden layers ought to satisfy if one wants to hope to learn the dictionaries in an unsupervised manner given the Ys. Okay. So moving on. Actually, this is the slide that I just made the comments about in terms of the sketch of the proof. Induction using results, where at each step of the induction, you apply shallow dictionary learning theorems, basically. That's how the proof works. Now, one important thing that I want to move on to before I show you how I applied this to simulated data and data from image patches is the following. So let me come back a couple of slides. So one important property that you see everywhere in the shallow dictionary learning literature is that for me to hope to be able to learn, let's say this product matrix in my first step here, right? The product matrix ought to satisfy some isometry type properties, okay? So in typical classical dictionary learning, this is not a product, this is just a single matrix. As long as it satisfies some RIP orthogonality like properties, I can learn it using some alternating minimization procedure. So one problem I needed to solve in coming up with my result is what conditions do I need on each of the matrices so that their product satisfies RIP? That's what I want to go through next before I show you some results. So the point there was that coming up with the result, one of the results in my paper, is not simply applying shallow dictionary learning results in a sequential fashion. You need to come up with some conditions under which these product matrices satisfy RIP type conditions. Okay, so let me first tell you, for those who have not seen RIP, what this means, and I'm going to do this in a very, very informal fashion. So an informal definition here that is in one of Verschinen's very nice treatise on random matrix, non-asymptotic random matrix theory is the following. Give me a D by R matrix A. In words, it satisfies RIP of order Sx if it preserves the lengths of sparse vectors. This matrix acts like an isometry on vectors that are Sx sparse, okay? And pictorially, this is how you show it. So one result that's very well known is that if I pick the A to be a dense matrix and its entries to be IID random sub-Gaussian, you could show that these matrices satisfy RIP. And I show this pictorially. You start with a sparse vector and restrict it to these sparse vectors. The norm of Y is approximately that of X. They preserve norm. So one thing that I had to show, which is not too difficult, but needed some work, was the following. That if you pick these matrices A to be column sparse matrices with a fixed sparsity level. So one thing that's important in my deep sparse coding model is that you start with a sparse vector and that you have to maintain certain amounts of sparsity after every successive transformation, except for the last that gives you the image. And for that to work, I needed to force the matrices, the intermediate matrices, to have a fixed sparsity level. So one thing I had to show is that if you have column sparse matrices with random sub-Gaussian non-zero entries, that these matrices also satisfy RIP, okay? And the reason why this is not necessarily a trivial generation of the dense case is that as soon as you ask for a fixed sparsity level per column, the entries become dependent to each other, okay? So going from this, informal theorem here that I have in my paper is the following. Is that, so remember my deep sparse coding model here. I start with a sparse vector, goes through a sequence of sparse transformations, except for the last one, A capital L here, right? And I'm going to denote the product matrices. So A1 times A2, A1 times A2 times A3, and so on and so forth. I'm going to denote that using this notation here. Actually, I said that wrong. If I pick any L here, the matrix that takes me all the way to capital L, those product matrices, I'm going to use this notation here to denote them. So an informal theorem in the paper says that if each of the intermediate matrices satisfies RIP and they're column sparse, then these product matrices will satisfy RIP. What's the intuition here? The intuition here is that you start with a sparse vector, and I just told you in the earlier slide that if this is a sparse matrix with fixed sparsity level, I can show that it satisfies RIP, meaning that it preserves length. Well, if the next matrix satisfies RIP with a sparsity level that depends on the sparsity of the product A1 times X, then the next matrix will also preserve length, and so on and so forth. That is the intuition. Pictorially, it looks like this. I start with a sparse vector, okay? And the matrix A1 is column sparse and also satisfies RIP that depends on the sparsity of X. So the first assumption is that A1 preserves length, which means that the norm of X is roughly the same as the norm of Y1. Then I'm going to force A2 to satisfy RIP with a sparsity level that depends on the sparsity of the vector Y1, which in turn depends on the sparsity of the columns of A and the sparsity of X. If those two conditions are satisfied, then the product matrix here will preserve length. Okay, great. Now I want to move on to seeing how this works in simulations and in an application that I did in my paper to natural images. Okay, so in the simulation, so here's what I did. And I did it for 2 layers for computational reasons that I can dive into perhaps in the Q&A session. This is alternating minimization. So to solve the sequential alternating minimization problem, you have to be able to solve a lot of convex optimization problems in parallel. We don't have a lot of infrastructure to do this in a clean fashion, as far as I know, in signal processing. So one nice thing about the autoencoders versus alternating minimization-based dictionary learning is that you can just throw the autoencoders on GPUs and parallelize that very, very easily using things such as TensorFlow and PyTorch and so on and so forth. But back to what I did. So the dimensions that I pick are the following. I had a vector X that is 800 dimensional with a sparsity level of 3. The matrix A1 leads me to a 200 dimensional space and also has a sparsity level of 3. I picked the entries to be Rademacher, so plus or minus 1 with a scaling of 1 over root 3 to make sure that they have length 1. And the matrix A2, as I've mentioned, can be a dense matrix. So I picked these entries to be IID Gaussian, and it led me to a 100 dimensional space. I used on the order of 7,000 training examples. And what you can show is that by applying the sequential dictionary learning algorithm that I showed you, that you actually learn the matrices A1 and A2 in an unsupervised fashion. So how am I assessing the error of the learning here? So what I'm going to do is, so A here is my true dictionary that I used in my simulation. A hat is the estimated dictionary. I'm going to compute the angle, the normalized angle between my true dictionary and the estimate at every iteration of my sequential dictionary learning algorithm. And if my algorithm works well, that angle should converge to 0. And this is what this picture shows, that as a function of iterations of my sequential dictionary learning algorithm, I'm able to converge to the true dictionary that generated the data to within some tolerance here. And so in my paper, there's another algorithm that is not the one that I presented here today, which learns the dictionaries in the opposite direction. And I call that the backward factorization algorithm. And it has a different analysis. So I urge you to check out my paper if you're interested in that. So in terms of applications to some real data, I did not do anything that has to do with classification. I'm going to conjecture at the end of the talk how that could be done. I just want to check real quick how much time I've got. Okay, I think we're doing good with time. So I did not do anything with classification, but I will conjecture at the end of the talk as to what I think might be happening or what the implications of what I'm talking about might be from a classification perspective. So applications to natural images. So what I did here, with the help of one of my grad students, Bahare, is that I took 5,000 patches from 5,008 by 8 patches from this popular BS Berkeley dataset, image processing dataset, BSD 432. Okay. And the first thing I did, so what I wanted to do was the following, right? So one question you might ask me, right, is my model looks linear. And by the way, it's not, because I'm forcing sparsity at every step, but we can come to that in the Q&A session. You might ask, hey, the model is linear, and why do I want to learn a sequence of transformations? Why don't I just learn the product matrix? So this is what I wanted to, this is related to a point I wanted to make here. So the first thing I did is I learned a shallow model where my matrix A is 64 by 256, and I assume the sparsity level of 5 on the axis. Again, the details of how I did the experiments are in my paper. I don't want to focus on that. All I wanted to do is to show you the columns of A that I learned, these filters that I learned, which have something that in image processing we're very used to. They look like edge detectors that are oriented in different fashions. But the thing that I want to point out here is that the number of parameters here, the number of unknown entries of A is on the order of 16,000. Next thing I did is, for the case of the 2-layer model, the 2-layer deep-sparse model, I did the following. I picked A2 to be 64 by 64. Dense. I picked A1 to be 64 by 256 with columns that are 2 sparse and the x's to also be 5 sparse so that you have the same complexity of the x's as you have in the shallow model. One key thing that I want to point out here is that you can do the math. There's a third less parameters to learn in this deep sparse model than there are in the shallow model of top here with a product matrix of the same dimension. So that's one. That's one important part, that this deep sparse model has fewer parameters to learn. And you can show actually, and I make this argument in my paper, that the reconstruction error you get by using the product matrix in the deep sparse model is on par with that you get using the shallow model here, which suggests to some extent that the shallow model here might be over-parameterized for this particular data set that I use, right? And what I'm showing you here is the matrix A2 on the left here, which is 64 by 64, the filters that I learned, edges again that are much cleaner than those that I learned in the shallow case in the top model here. And I'm also showing you the matrix A1 that I learned, which has sparsity levels of 2. The next thing I'm going to show you is for this 2-layer model, the combined matrix A2 times A1. And it looks like this. So the interesting thing here is that, and I did not do a proper visualization to show you this, but what I noticed when I did some exploratory data analysis is that, so the product matrix still look like edges, they just have less complexity or less fine orientation compared to the ones that you learn with the shallow model. And another comment that I've made here that I do not have any theory to substantiate, but through discussions with colleagues and with my students, we think that this one be my intuition that might be going on here is that if we were to apply this to classification, and that's potentially our next step, that there might be some implicit regularization that the deep sparse coding model does. Because it has fewer parameters, right? You could basically think about that as some form of regularization that might help better generalization in classification tasks. So that's all I wanted to show in terms of application to natural images. I'm going to conclude here and open it for questions. So what I've talked about here is dictionary learning for what I call a deep sparse generative models. And what I wanted to come up with were conditions that enable one to solve this deep dictionary learning problem or this deep dictionary recovery problem. And these conditions look like RIP, restricted isometry property, which basically mean preserving the lengths of the sparse representation at every sequence in the deep generative model that I started with, to another important condition here, one of which is sufficient, but not, actually both of them are sufficient. I don't want to claim that they're necessary, is that I start with a sparse vector. I'm going to force every intermediate representation to be sparse. That's number one. And the way I do this is by forcing the columns of the matrices, the intermediate matrices, to be sparse. Another thing that I came up with here, where I tried to give you some intuition as to how we could use that to make statements about how much data we need to train not only the deep sparse model, but the associated autoencoder architecture that I showed you. And finally, one of the algorithms in my paper for sequential deep dictionary learning problem actually constrains the relationship between the hidden layers of the network, which might give some prescriptions as to how we could design these deep sparse autoencoders. And finally, I'm going to conjecture here before I open it up for Q&A. So the thing that I think might be going on is the following, and this is related to neuroscience. There's a theory in neuroscience that goes back to a paper by Horace Barlow in 1969, is that one thing, so in neuroscience, we don't think of the matrix A2, we think of the transpose. You give me Y, the brain takes A2 transpose Y to find the sparse representation here, and then it takes A1 transpose the sparse representation here to find the next sparse representation. There's a theory out there of hierarchical sensory processing in the brain that says, and as far as I know, this has not been verified, that what the brain might do is that it might be trying to obtain representations of the input Y that are sparser and sparser. So because of my generative model here, I start with a sparse vector. One thing you should notice is that sparsity degrades every time I go through one of these sparse transformations. But what I'm suggesting is that it might not be a bad thing, because if the sparsity here is worse than the sparsity here, it might be related to the theory of sensory processing in the brain that says that you start with your input here, image impingent on the retina, you obtain a sparse representation, and you successively try to sparsify it the deeper you get inside the brain. So, and why do I think this might be important? I think this might be important in classification tasks. If you think about using each of the intermediate representation for classification, the one that I get at the deepest layer in my model here is sparser than all of the other ones. Could it be that basically what I'm doing is I'm extracting features that are more and more useful for my classification task? This is just a conjecture. I have not verified this. This is something we're excited to look into in my lab. And with this, I'm going to conclude. Well, I already concluded. The first paper here is the paper that talks about everything I've discussed today. And in my lab with my students, we've been looking at how can we use these insights now to train sparse autoencoders. And these are relevant papers in that direction. Thank you for your attention.
Thank you so much for that great talk. We have questions from the audience. The first one is, for products of matrices that keep the RIP structure, won't the sparseness requirements force the dimensions of the intermediate A's to grow to keep the columns sparse? Hence, you might get an expansion of the internal dimensions.
Yes, that is correct. That is correct. I believe that is correct. Actually, give me a quick second to just look at my picture again. Yes, assuming I understand the question the right way, that is correct. There is an implicit assumption of expansion here in my model, except at the first layer. But there is a subtlety there in the question that I love, but the short answer is yes, that is correct. There's an implicit expansion the deeper you go in this particular model.
And then another question for the audience, which you promised us you'd answer in the Q&A. Can you expand why this isn't a linear model? How the sparsity?
This is something I've been struggling with, which is the following. So I start with the sparse vector here, right? I force each of the intermediate matrices to be sparse, right? That cannot be a linear process. So it's the same reason that, actually, to answer that, let me forget about the deep case. It's the same reason that the model y equals ax, this sparse representation model, if you look at it benignly, it looks like a linear model, but it's not a linear model. The reason being that if I give you two x's and you add them up, you don't get a sparse vector of the same length. So it is not a linear model in that sense. I'm not sure if that answers the question. That it looks like a linear model, but because of that requirement of sparsity, if you just go through what it means for something to be linear, like in linear algebra, it violates those constraints, right? Because the sum of sparse vectors is not sparse, not of the same level of sparsity that you started with.
As if they don't lie in the same subspace.
Exactly, Gal.
Okay. So we have another question from the audience, but Renee has the same question. So Renee, if you want to ask it.
Yes. So I wanted to expand on that question about whether you need to increase the dimensions and why the RIP holds. So in particular, I was thinking, well, if X is sparse, and then I want to apply a linear transformation to X, will the result be sparse? What are the conditions on A under which this will be the case? And whether I can achieve that deterministically, whether there is a class of matrices that achieves that, or whether I can do that with high probability for matrices whose entries are drawn from some distribution, and how that relates to the dimension. So I wanted, my first line of question is, could you be more precise as to under what conditions this is even possible? And my second question related to that is, as you had proven, or you had a theorem right before this slide, I think, about the fact that the RIP is satisfied for products of matrices. And I got curious about how the independence of the sparsity patterns gets affected, because if everything was independent, right, I begin with a sparse X and I get another sparse, and then I repeat the process. But
Yeah.
as it turns out, right, all sparsity patterns are related with each other because
They
they
are.
all depend on the first one.
They are, and that's
So
something I've
I
swept
have
under
a
the rug.
difficulty understanding why it would be true that you can get RIPs with so much correlated, right?
So one way I can answer the question, let me answer the first part of the question. So the first part of the question is, so, and it's related to this slide here, this informal lemma here is, so the only claim that I'm making in terms of RIP matrices that preserve sparsity is this informal lemma here. If I pick a column sparse matrix A with random sub-Gaussian entries, fixed sparsity level, right? I can show that this matrix here satisfies RIP. As to whether they're deterministic construction, I don't know. I don't have an answer as to whether you even need the matrix here to have sparsity across the columns. So again, there's work by Jeremiah and his colleagues that use this concept of co-sparsity. So unfortunately, the only answer that I have for you here is that with high probability, if I have a column sparse matrix with fixed sparsity level, that is going to satisfy RIP.
Could you be more precise? Namely, for me, column sparsity of a matrix means that the number of non-zero columns is small. But from the picture, it appears that you're saying that each column
has a fixed sparsity level. The columns are independent, and each of them has a fixed sparsity level.
Okay.
Can I follow in on that? Because I think I have the same basic confusion, and I'm still a little confused. By the way, it's great to see you, and thank you for the talk.
Yeah, good to see you, Adam.
It's if you look at the conditions for RIP and you look at the conditions between the sizes of the matrix, right? The number of rows, the number of columns, the sparsity, there's that coherence factor. And if both A and the basis of X are sparse, that coherence is going to be high. So how come you don't suffer that limitation that forces your number of rows to be very high?
So I'm not sure what you mean by the coherence here. So here I'm assuming that X itself is a sparse vector atom. So I don't have an assumption that X has a sparse representation in the basis. Does that make sense?
Well, then the sparse representation would be in the trivial canonical basis, right?
In which case, because by construction, because this matrix has IID columns that satisfy this RIP condition, right? Those so rows of A and my canonical basis will be orthogonal with high probability, basically.
No, but the highest coherence between any row of A and one column of the identity matrix would be higher than if that same energy was spread out throughout the entire row, right? This is why you can't sample sparse in time signals with random sampling in time. You have to do random sampling in frequency or something. It's just going against my intuition. I'm sure there's an answer. I can't picture it.
That's something I would need to talk about, to think about a little bit, Adam, and we can talk about offline if you would like. But going back to Renee's question, right? So the first statement was that if I pick A such that its columns are IID, each column has a fixed sparsity level, let's call that SA, and I pick the non-zero entries to be random sub-Gaussian such that the columns of A are normalized, that will satisfy RIP with high probability. And because I've picked the columns to have a fixed sparsity level, I have an upper bound based on the sparsity of X and the sparsity of the columns of A on how sparse Y is going to be. Now, going back to your second question, Renee, which is something that I have to think about a little more. I think the statement that you're making is that now Y has more sparsity as an upper bound than X had, right? And that this should put constraint on the RIP properties that the next matrix should satisfy. And the answer is yes, Renee. And the statement that I can make here that I'm happy to talk to you about offline is, in some sense, because all these results are with high probability, you're dealing with humongous matrices here for this to work well in a non-trivial fashion. I would have to have these matrices be really big for this to work well in a non-trivial fashion.
So yes, but those are two independent concerns, and let me try to ask questions about both.
Gotcha.
Concern number one is the dimension keeps growing. So if you want to implement this in like the least algorithm, that you want to do many layers in order for the sparse encoding to produce a good solution, then you will just get an explosion of dimensions. But the second one, what I was actually asking was, what is the sparsity pattern of Y? Let's say that the sparsity pattern of X is that it has S non-zero entries, but the choice of those S is, I can choose any choice S out of the total. But once I multiply by A, depending on the distribution of A, the sparsity pattern, the distribution of that for Y may not be, all patterns might not be equally likely. I don't know, depends on, and therefore the same style of theorems and the same styles of proofs might not apply to get the RIP.
I think they would, for the reason that all I need is an upper. So irrespective of what that distribution is, I have a fixed upper bound on the sparsity level of Y. So as long as the next matrix satisfies RIP for that fixed upper bound, I'm fine. That's the claim, right? So RIP, as far as I understand, RIP does not care about the distribution of the entries of the sparse vector that is the input. It only cares about the sparsity level of that sparse vector. So it doesn't really care so as far as X is concerned, RIP is deterministic, right? So these high probability results that we usually have are because we pick the A matrix to be random, not because X has some randomness property. So all the probability here for the RIP is because of A, not because of X.
Well, but say for the sake of argument, let's say that for whatever reason, A would always map X to a Y vector that the first so many entries are non-zero and the other ones are always zero, right? So that means that you could get much, that you would probably design the algorithms for the remaining layers in a different way.
I see your point. I see your point now. So I agree.
That's an extreme case and probably never happens, but
I agree that in some sense, what I've presented here, or my results are very general and they're not taking into account some of these constraints. But the aim was just to say that, hey, here's a generalization of regular dictionary learning that makes sense and that is associated with certain types of deep neural network architectures. And here are the kind of statements we can make for this generalization. So I agree with you that a lot of these results can be improved. But the attempt was to actually address the question of learning the dictionaries in this deep model, which to my knowledge had not been addressed.
This is a great discussion, but I would like to squeeze in one last question from the audience before we move on, and maybe you both can catch up on Gather later or offline. We have another question from the audience about initialization of A, or initializing deep learning versus dictionary learning that you commented on earlier in the talk.
So just about the thing that I commented on earlier.
Yeah, and how to understand in what way the initialization affects the learning.
So I mean, I come from a signal processing background, and again, from this dictionary learning perspective, at least from shallow dictionary learning, and I may be wrong in the statement I'm about to make, but I do not know of any result that say that if you initialize randomly, you can still learn the dictionary. So that's the context in which I made the statement that, to me, I don't really understand random initialization. So again, using this analogy between the dictionary learning problem and the autoencoder, to me, what this says is that if in dictionary learning, a lot of the results we have, or all of the results that I know, say that we should initialize closely in order to be able to learn. To me, that gives me intuition that for the associated neural network, it actually makes sense that I would need to initialize closely to actually learn. So for example, in image processing, the signal processing people know this really well. I mean, how do we initialize? We usually do things such like the DCT, right?
Right.
And things like that, right? So that's the context in which I made that statement. Maybe
this is related to in earlier deep learning, we used to do pre-training to initialize our weights at a more closer solution to the right solution.
Exactly, exactly.
Okay, and one last question. Do you think from the audience that maybe the adjacency matrices of expander graphs, which are like random matrices but have deterministic constructions, could be a deterministic model for these kind of column sparse matrices A? To get a rectangular matrix, you could use a bipartite graph.
That's a great question. Let me make two comments related to that. First, the first comment is, as far as I know, this connection between sparsity and ReLU networks has not been considered from the expander perspective. So in signal processing, we have the expander folks and we have the more like mutual coherence RIP folks. And the mutual coherence RIP folks, as far as I know, are the only ones who made the connection to neural net. So there is room there to assume now expander type matrices and make a connection to ReLU nets. Number two, I would have to think about this because as far as I know, for expander graph, they don't satisfy RIP in the sense that I've defined here, not in the L2 sense. They satisfy a different form of RIP, as far as I know. So using those different forms of RIP, I think you could make similar statements to what I'm talking about here. But that is a great point. And yeah, that is a great point that I actually made recently to one of my students.
Thank you very much for the great talk, and both you and Renee for the lively Q&A session.
Thank you for the invitation. Yeah, thanks again for the invitation.